This is Jeff Mucci with RCR Wireless News. Thank you for joining us today. Our topic today is detecting, identifying, and locating RF interference. And our speaker is Eduardo Inzunza, who is the Global Head of Business Development for the RF Division for JDSU. Before we get started, I'd like to cover a couple housekeeping items. Firstly, this is estimated to be a 1-hour webinar, which will include 10 to 15 minutes for Q&A. During the course of the presentation, we welcome questions to be submitted using the question button on your control panel. And to the extent we can, the speakers will answer some of those questions or take them offline and answer them directly. We also queue up questions and answer them during the Q&A session. A link to the presentation will be made available to all the registrants and attendees after the webinar is completed, and that will be distributed within about 24 hours. Before we get started with Eduardo's presentation, I would like to take a quick poll of the audience just to get a feel for the audience experience with interference, RF interference particularly. So if you would, please cast your poll in our quick poll depicting how frequently you experience the presence of interference, daily, weekly, monthly, or rarely. So we'll leave this poll open for 30 seconds or so, and then we'll turn things over to Eduardo. Eduardo, you're in California today, right?
Yes, that's right.
Oh, good. Well, thanks for your patience while we go through this this quick poll. And I will share the results before we get started. We've got about 65% of the attendees voting. I'll wait till it gets up around 70 to 75 and then share the results. Okay, we just passed 70%. If you haven't voted, please do so. I'll leave the poll up for another 5 seconds. Okay, last chance. Cast your vote. Okay, we just passed about 80% Eduardo, so I'm going to go ahead and close the poll now and share results. So you can see the results there. Daily 16%, weekly 24%, monthly 31%, and 28% rarely. So Eduardo, when we come back to the Q&A session, we're going to talk a little bit about how that compares with what you're seeing. So at this time, I'd like to turn things over to Eduardo. Eduardo, thanks for your time today.
Hey, thank you for the introduction, Jeff, and welcome everyone to this webinar of RF interference. Just a couple of disclaimers, I guess. One is that this presentation and this material, it's going to be primarily around of interference in cellular networks. And I have a few examples here in the presentation, which again, the view it's on cellular carriers and how interference might affect the cellular communication. So first, I'm going to go through the basics, just a quick overview of RF interference. And then I'll be covering the three main aspects of interference analysis, which are the detection, the identification, and the location of interference. So let me start with an overview of RF interference. So the RF spectrum is basically heavily used by multiple users. That can be licensed users or unlicensed users, and they're delivering different type of services, and in some occasions these signals overlap, causing interference, and obviously interference will have a negative effect in the service, reducing, for example, the network coverage or even the mobile throughput based upon where the interference is it's affecting the signal. So, for example, licensed transmitters can be reusing frequencies on different carriers as a transmission of GSM and WCDMA, for example, in band 850, where a small change on the configuration planning or even a frequency drift of the cell site might cause interference. Another example of licensed transmitters can be the presence of broadcast TV, where they are transmitting at frequency between 55 to 1 gig, and that basically overlaps with services on the, for example, 700 and 800 bands. Now, on the contrary, cellular services might actually leak into the cable TV infrastructure, and that will cause interference with TV channels. So we can view it in both perspectives. Now, for unlicensed transmitters, there are things like jammers used in conferences, or amplifiers, or signal boosters used in some neighborhoods, that, or even illegal transmitters. And they also significantly contribute to RF interference. Now, RF interference can also be caused not only by the overlap or collision of carriers transmitting on the same frequency, but also by, let's say, RF products or RF derivatives. For example, a product can be a signal such as a harmonic or a spurious that, that basically is generated by the radio if the radio doesn't have a good shielding. There are other instances of interference where the interference might be even inside of the cell site due to improper conductivity on the feed line. That's typically known as PIM, or passive intermodulation. So, but in any case, regardless of what type of interference exists, if the source is external or it's internal, it is really important to go through these three main steps, or three main aspects for interference: the ability to detect that there is interference, the ability to identify what type of interference that is, and then finally to locate the source of interference. Now, interference can be experienced on a cellular network in the downlink, or the signals transmitted by the cell site, but also on the uplink, which are the signals transmitted by the mobile. It is, however, the uplink which is more susceptible to interference, since these devices transmit signals at a maximum level of about 23 dBm according to 3GPP. That's roughly about 200 milliwatts, which is relatively low if we compare that to the signals transmitted at the cell site, which normally they're transmitting at about 43 dBm or 20 watts. So basically this means that power level of a mobile is about 100 times lower than a cell site. So it is common to see amplifiers, for example, on cell sites, but if there's any interference in the uplink, those amplifiers will amplify the entire signal, which means the amplification of the uplink as well as the amplification of the interference. Now, here in this example, actually I have three examples here showing interference in the uplink. The first one is on CDMA, the next one is WCDMA, and finally the last one on the right, it's LTE, where the higher yellow trace that shows the uplink traffic, and the lower orange trace that shows the presence of interference. The source of interference in cell sites can be, as I mentioned, external, due to other transmitters, or the other devices that generate noise, right? So it can be, as I mentioned, the leakage, RF leakage in radios, or passive intermodulation. But again, regardless, it's really important to look into the type of interference. First, to have that ability to detect, identify, and then finally to locate where the source of interference is. Now, on this last aspect of locating the interference, so after the interference is detected, traditionally the next step was, as a troubleshooting step, was to do what it was called an interference hunting, or the ability to locate the source of interference, which it's a process that requires a directional testing on a spectrum analysis. This is basically being done with directional antennas, And these tests actually require making 3 different tests in different geographical positions. So then a triangulation can be made, and then basically with that triangulation can be defined which is the area in which most likely the interferer is located. So this is a time-consuming process, and even it might be more challenging if the interference is intermittent, or even if the interference is mobile. So it is really highly recommended to perform interference identification first, and this basically involves signal analysis, or let's say modulation analysis of the interference, because it might give us much more information. Actually, we can avoid the entire interference hunting process if we can identify the interferer. And actually I have a couple of examples that I'm going to be presenting on the webinar. Now, in cases where interference hunting is required, then it is going to be really important to have a real-time or even an immediate triangulation assessment or a triangulation process in order to promptly identify the location of the interferer and basically reducing the time in which it's affecting users. So this is the a brief overview of what is interference in general. What it's more, the area that is more sensitive, which is basically the uplink or the communication of the mobile to the cell site, and the complexity or what it's required to locate external interferences. Now I'm going to dive into the first process, or first step of the process, which is the ability to detect interference. To detect interference, basically it's used a spectrum analyzer. So we have, with spectrum analysis, we have a visibility of the overall spectrum. And here for spectrum analysis, it's important to highlight 5 main factors to properly detect interference. Those are attenuation, preamplification, trace control or trace management, what's going to be the frequency span that we're going to be testing, and also the resolution bandwidth or the filtering that the spectrum analysis will have. And these factors or these parameters are basically related to both components. Those are the power level and also the frequency component. So in terms of the power level, interference measurements are typically performed over the air, so the signals are in a relative low power. For instance, power levels should be properly adjusted in order to have enough sensitivity to test the uplink, as I mentioned. And the uplink, the recommended, let's say, noise floor to analyze the uplink traffic, it's as low as negative 120 dBm. So any noise, any filter, any interference that we might have at neg 120 or below, it's acceptable. Anything that is higher, it might be concerning. Now, this visibility can be achieved by first removing the attenuation that we might have on the spectrum analyzer, and activating a preamplifier, and basically that will give us about 10 dBs of more sensitivity, reducing the noise floor about 10 dBs. Now, the adjustment of the resolution bandwidth, it's key because it improves 2 different aspects. One, it's going to improve the sensitivity, as well as it's going to improve the frequency granularity, or how many measurements or how many samples the spectrum analysis will take. So if we want to detect narrowband signals, it is important to have the right setting on the resolution bandwidth. Now, at the same time, it is important to notice that a low resolution bandwidth implies a high number of measurements in the same frequency span. So these will increase the sweep time of the spectrum analysis. So for example, if we're interested in looking for an uplink of LTE, and the LTE signal is 10 megahertz. So it is recommended when we are making these sensitivity adjustments to have a frequency span of about 12 megahertz. Basically, that will give us full visibility of the uplink without compromising sweep time or test time. In this example that I'm showing, on top we have different traces. The top one, the first trace that I'm showing at about neg 82 dBm, that basically is with a presetting of a 10 dB attenuation with preamplifier disabled and with the resolution bandwidth of 300 kilohertz. Now, if we make these adjustments, as you will notice, the noise floor goes all the way down by just removing the attenuation to 0 and then enabling the preamplifier and lowering the resolution bandwidth to 10 kilohertz. All of a sudden, the noise floor went all the way down to neg 122, and then we have visibility of what's happening on that frequency span. So again, these are just some of the techniques. I'm going to be talking a little bit more about other aspects of looking at the uplink, for example, or even have a good signature of the noise floor. That's more related to the trace control and trace management. So first, I'm gonna give you another example, a case in which here the proper adjustment of the resolution bandwidth and video bandwidth is important to uncover or to detect interferences. So in this example, the upper trace in orange was made with a resolution bandwidth of 300 kilohertz, detecting the presence of cellular traffic in 3 different frequency blocks in the 800 megahertz band. The first one is GSM, then a couple of carriers on double CDMA, and finally some carriers on CDMA, which in this trace there's no apparent interference detected in any of these channels. Now the resolution bandwidth was adjusted to 10 kilohertz. That basically lowered the noise floor, and also the video bandwidth was set to about 10% of the resolution bandwidth, or to 1 kilohertz. So basically that will clean up any noise variation that we have on the test, and as we can see, we were able to identify now interference in the double CDMA carriers. So again, it is important to make those adjustments, and if there's any area of interest, we can just narrow the frequency span and perform the test. Now, if we go through that process of we have identified an area where we might have an interference, and we need to do an additional assessment or additional testing on what that interference might be, then that involves the control or the management of traces. And this control management of traces basically involves the ability to hold the maximum power on the measurement or on the frequency span we are testing, or to hold the minimum power level of the trace. So what is this is important? For example, here, the orange trace that I have in the middle, basically this is the type of trace that you get in real time, which is not a clear representation of any type of a cellular signal. However, when the power level is set to maximum hold, this is illustrated on the upper yellow trace, it becomes a close representation of a 200 kilohertz signal, such as GSM, which, due to its time-based structure, is not constantly transmitting power. So that's why we see on a real-time trace that power variation because it's like a train sequence of the different time slots on a GSM signal. Now, another case which is convenient to have a minimum hold is with the holding the minimum power of the signal, and this is basically the example that I'm showing as the lower white trace, which again kind of maintains the low power that the signal has exhibited for the amount of time that we've been doing this test. And this ability basically will help to differentiate the noise floor, the noise level, and even the presence of interference from uplink traffic. For example, uplink traffic is variable, and it's actually transmitted by demand. If a user wants to send some data, then we will see power changing. So, in a way to differentiate what is uplink traffic from noise, a good method of doing it is just by holding the minimum power that we're seeing, and basically that's going to be a good representation of the noise floor. And even if there's any interference present, we're going to be able to capture that interference. Okay, so a different aspect now is with signals that are based on time. So most of the times we have been involved with, for example, 2G, 3G signals, which GSM, it has a time domain component, but in 3G with CDMA, EVDO, or double CDMA, didn't have a time domain component. So all the measurement was made on a frequency based. However, with signals that are time domain, such as LTE TDD or WiMAX TDD, it is important then to look into the time aspect of these signals. And the reason being is that the downlink and the uplink, so the signal basically is transmitted on the same frequency, and data of uplink and downlink is transmitted on the same frequency. The distinction between them is based on time slots. So there's a time gate for the downlink, and then there's a time gate for the uplink. So detecting interference in time domain signals require that interference will also be made on a time domain basis. So just setting the test on the center frequency of the signal, and then have the analysis made on a transmission time, for example, of 1 frame, this will effectively differentiate the time slots for uplink and downlink. So this will allow to have a better visibility on the uplink and capture possible interferences. For example, here we have a WiMAX TDD signal that is transmitted at 2.3 gigahertz, and we're analyzing this signal for a time of 5 milliseconds. And as you can see here in the first three time slots, or 3 milliseconds, those are assigned to downlink transmission, whereas the last 2 milliseconds are assigned to uplink traffic. And in this instance, there was no traffic being transmitted, although we were seeing some interference in the uplink. So it is important for time domain signals to have these different aspects, and instead of analyzing the signal on a frequency domain, to make it on a time domain, which is going to be again important and very applicable when there are services such as LTE based on TDD or time division duplex. Now, I think another aspect that is important in terms of interference is to do a proactive approach on interference and perform what is typically known as a spectrum clearance. So here, spectrum clearance basically, in principle, means that The spectrum that was assigned for a specific service should be clear before launching that service. And to verify this spectrum clearance, it is typically performed with just a spectrum test, but performed through an extended period of time. This is because the intent is to ensure that there are no intermittent signals present on the assigned spectrum. So, and the simplest and fastest method to perform this spectrum clearance test is by defining a power level mask, where this power level mask basically will indicate what's going to be the maximum acceptable noise level on that spectrum, and as well is going to allow us to exclude any signals that are in service. Here I'm showing two examples of spectrum clearance, where the first covers a 50 megahertz in the 700 megahertz band, where the maximum acceptable power in this example is set to minus 100 dBms. And it excludes the presence of these two LT signals, one at 739 megahertz and the other one at 751 megahertz. The other example, the example on the right, covers 100 megahertz in the 2.1 gigahertz band, where here the maximum acceptable power was set to minus 114 dBms, excluding 12 carriers, 12 double CDMA carriers. Now, this power mask method will simply provide a pass-fail indicator, and if at any given point in time any signal exceeded the mask, then we will get a flag or an index of the event where the signal exceeded the mask. And we'll be able to have additional information on those instances, like the position and even the time of each event. And these methods can be basically implemented on an unattended manner. So we can leave the test running, and then basically that will reduce the processing time, processing and testing time. Now, a problem that exists with interference is with those interference that are intermittent, that basically they appear, they're created in some period of time, and then they later on disappear. They're not constant in time. And the best way to detect these intermittent interferences is by performing and even recording a long-term spectrum analysis, and actually presenting that behavior through time, or that histogram, and how the spectrum changed through time. And this measurement mode is often called a spectrogram. So this spectrogram registers the spectrum activity on a color scale that corresponds to the signal power level, and presents the measurement across time. So when there is any change in power level, it will be clearly detected by a different color that we see on the spectrogram. In addition to the spectrogram, we can get additional information to locate intermittent interferences, because it will also provide with the position and the time of that specific instance where an interference took place. For example, here the test was performed on a frequency span of 30 megahertz, and we were observing activity from GSM, WCDMA, and CDMA carriers, and we noticed an intermittent signal were detected as a color change in time between green and blue. So this spectrum is shown that actually corresponds to the measurement time indicated in the green marker. So we have a small marker that actually it can be scrolled up and down the histogram of the spectrogram, and as we scroll, then we can have the spectrum analysis of that specific point in time. So we're going to be able to detect at what frequency the interference happened. In this specific case, we have that marker or that timeline or time cursor that an interference happened on the 27th of September at 8:15 in the morning. So these will give us that information of and to have some trends of at what frequency the interference is happening, and if there's any trends on at what time of day the interference shows. So it's very common to perform these tests in matter of days to basically detect all those intermittent interferences. And the ability to make these tests on an unattended manner, and then later on to do a post-processing or post-analysis is really important. And actually here, all the measurements was done with the spectrum analysis, and it was then post-processed, and actually that's what I'm showing as the diagram on top. So it will give us a better visibility of the time, frequency, and power, basically what was the activity on the spectrum. Again, it's very useful to detect intermittent interferences. Now, a different source of interference might be caused internally. And one of that interference might be the feed line itself. So the feed line is that physical layer, physical link between the cell of the cabinet up to the antenna. And these feed line can have some improper conductivity, such as a fracture joint, or the use of different metals in the connectors and the jumpers or in the cables, that when two carriers are combined, for example, GSM and WCDMA, they're combined and they're transmitting through this faulty feed line, then interference will be created as an RF product or a derivative of these combined signals. This form of interference is typically known as passive intermodulation, since it's being created by passive devices or passive components. So in this example, I'm showing that we have a WCDMA carrier. For example, it's in channel 4458, which has a center frequency of 891 megahertz. And then it's combined with a GSM carrier, channel 128. That's a center frequency of 869. So when these two carriers, these two signals are combined and are sent on the same feed line, these conductivity imperfections or conductivity problems that might exist on the feed line, then will create these products. And here I'm just showing the third intermodulation, or the third product that was obtained by the combination of these two signals. And this third product, or third intermodulation, basically generates a signal at 846 megahertz, which basically is part of the uplink band of GSM, which basically means is that PIM then is going to be affecting uplink traffic. Now, so this is another way of interference. So what's going to be the best method to detect that there is interference internally on the cell site? More specifically, there's PIM. So to detect PIM, it exists a technique which the PIM can be detected just by using the spectrum analysis and controlling the transmission of the radios. So first, to register, let's say, a test reference without PIM, and then to have both signals transmitted, so we can have PIM present and have the relationship that exists with and without PIM. For example, the reference without PIM can be obtained performing a spectrum analysis, and we have to have the sensitive conditions on the spectrum analysis, the ones that I briefly mentioned before, that involves removing attenuation, enabling the preamplifier, and setting the right resolution bandwidth. So we lower the noise floor of the instrument, and then one of the carriers will remain active. For example, in this case, it's going to be double CDMA, whereas in the case of GSM, it's going to be shut down. So here we're going to have our reference level of the noise floor of the cell site. Then, so that's our reference. Then the GSM carrier can be activated, and the combined signal will go through the faulty feed line. A PIM will be generated, and then we can capture the measurement on the spectrum analysis and compare it to the reference and see if there was any difference. And this is an example, and it's important to have a reference because the PIM can be caused or can be created by a third or a fifth or a seventh product, which is hard to detect. It's hard to identify that truly is PIM because in some instances the noise floor just changes. And again, if anything goes above 120 or negative 120 dBm in the noise, then that causes problems with the uplink traffic. So those were kind of the main aspects about the ability to detect interference. Now this next aspect is really important, and it's called in which way we can identify what type of interference that is. So I'm gonna use one example here where if we go through this process of identifying the interferer first, basically we'll reduce troubleshooting time, and even in some cases, the interference hunting will be eliminated. So this is a good example where if we have a signal identification capability, then we're going to be able to first identify which are the possible signals that can be transmitted on the same frequency as the interferer is being transmitted on. And then once we have that information, then we can have, or we can perform a modulation analysis to confirm that truly it's a modulated signal, and even beyond that, to have some of the specifics or the characteristics of that modulated signal. More importantly, the cell identifier, which basically means which cell site is transmitting that specific signal, which is interfering. So this example basically shows a double CDMA carrier. This double CDMA carrier is a channel 4360, center frequency of 872 megahertz. And as you can see, it's experiencing interference on its lower frequencies. So the first step is to identify which possible signals can be transmitted at that frequency. And as you can see here in this example, we're able to put a marker to identify the frequency of the interferer. That's about 869.5 megahertz, and then perform the interference identifier, and we basically get a list of the possible signals that might be present at this frequency. In this case, basically the first option that we have is that it's a GSM signal on the band 850, and it's more specifically channel 130 forward, which means it's a channel being transmitted by a cell site. It's a downlink signal. So with this information, then the next step will be to perform a modulation analysis. So basically, to look into that signal based upon the information that we obtained from the interference identifier and demodulate the signal. So here, for example, the signal analysis was performed on that same information that we obtained, the channel 130 of GSM 850. And it was confirmed that, in fact, it's a GSM signal. But in addition to that, we obtain the BISIC, which basically is the cell site identity or cell site identifier from where the signal is being transmitted. So in this example, the cell site is cell site number 36. In a similar manner, we can perform a modulation analysis on the WCDMA carrier that has been affected. We can obtain the modulation quality, and also we can obtain the cell identity or the scramble code of the signal. And in this case, it was cell number 267. So as a conclusion, we can see that in these locations, cell site 36 is transmitting a GSM signal on channel 130 that is interfering with cell site 267 transmitting a WCDMA channel in 4360. And basically performing these signal analysis or identifying the interference, promptly we obtained which type of signal was transmitted, which side was transmitting that signal, and then instead of going out and hunting the signal and spending a lot of testing time hunting it, just by doing this modulation and signal analysis, we obtain all the specifics that we need to resolve this problem. Now, there are instances where even with signal analysis, is not possible to identify the interferer. That's basically the case where interference is not caused by another cellular transmitter. So in this case, it is needed to perform a location or to locate the interference or to do an interference hunting. So this is going to be the next section. So here interference is caused by an external source and couldn't be identified as a cellular signal, so it needs to be located. And to do this, it's needed to go through a triangulation process. This triangulation process is made by making tests in at least 3 different geographical positions using a directional antenna. This will obtain, with this testing, we can obtain the direction from which the interference signals were received. So combining the information on each test point of position and azimuth or direction, then we can post-process this information and obtain the intersection area. And basically that's going to be the area where the interferer is located. In this example, the ability to have an interference finder that will obtain position of each test point through GPS and instantly perform the triangulation. In this case, it's indicated as a green circle. And this ability to obtain that information automatically from GPS and actually to perform the triangulation instantly greatly reduce the time of interference hunting, and actually it's going to help to identify intermittent interferences because the test time was significantly reduced. And in addition, with the assistance of GPS, once that we have identified that intersection area where the interferer is located, we can have a feedback information of where is our current position in the map. This indicated with a square icon that I'm showing it there as as a red square icon, that basically that's going to give us a perspective of the position in which we are against the intersection area or the location of the interferer. Another comment on another recommendation that we have for interference hunting is to perform all these tests in open spaces and in high places like rooftops. And the reason being is that it is important to avoid any signal reflections or any multipath, and that basically again will improve or reduce the test time. So I would like to just to highlight three key aspects of RF interference. The first one is that it is an increasing challenge because the cellular networks are not being decommissioned with new technology, but it's basically an overlay of signals. So still we have today 2G networks with 3G, with 4G. So these migration that we are experiencing from 2G to 4G is taking a long period of time, and that basically will affect the let's say the pollution that we have on RF and the risk of having interferences. And even with new technologies that we're seeing coming up, like in the small cells, there's an initiative of having a non-line of sight radios, which basically the communication between those small cells is going to be through RF instead of traditionally has been a DSL or a fiber. So again, it's just more transmitters that are occupying the spectrum. So it is important to have an automated and an unattended capability to make all these tests. But perhaps more importantly is to have a systematic test approach covering those three aspects that I briefly mentioned. One, the ability to detect interference. The second one, the ability to identify the interference. And finally, to locate the interference. Those are the fundamentals to perform an interference hunting or interference finding or interference analysis promptly to avoid problems. So having the right test tools to conduct these tests, to conduct those three aspects or three stages that I mentioned, if we have the right tools and we perform those tests, we can reduce the maintenance time, which basically nowadays we have less and less test time or maintenance windows or maintenance times with these increasingly number of transmitters that we have to take care of. And as a closing remark, JDSU have that capability of providing you with the right test tools to perform these tests. So with that, I would like to thank you all for participating, for your time on this webinar. Additional information of RF interference or wireless testing is available. You just need to scan that code I'm showing on the slide, and you're going to be able to get more information from JDSU Solutions. So with that, Jeff, we can go to the Q&A.
Okay, thank you, Eduardo. I do want to look back just quickly to the results from the first poll, and I'm going to put those up quickly. We asked the question, how often do you experience the presence of interference daily? We had 16%, weekly 24%, monthly 31%, and rarely 28%. I'm just curious quickly, Eduardo, how do those percentages compare with what you guys see in the market?
I think, if we just take an average, I think it's consistent. So we have some instances where people observed interferences fairly frequently. And there are some of the cases in which, actually I was in a case where people had interference and actually they were not able to to hunt or to eliminate that interference, and that was with an illegal transmitter, and basically the operator at that time, they couldn't go around and find and remove that interference, so they actually had to implement different ways of routing traffic and going around that specific location. But I guess that in general, I think it's consistent. In more specific, there are some areas that experience more interference than others.
Okay. I'm going to hide these results, and I'll pop up another, a second poll, and I just want to get the feel from the audience what the most common sources of interference they typically see. And I'll leave this open very briefly while we get queued up for the Q&A. And so again, I would ask the audience to spend a minute just clicking on the most common source of interference that they're finding. Eduardo, can you see those okay? Can you see the poll on your screen?
No, but let me
Okay.
open that up on the dashboard and see if.
That's okay. Why don't we go ahead and,
Okay.
If you want to leave your screen up, we got about 50% of the attendees voting. I'll leave it up for 5 more seconds. And right now we're running, the most common is signal jammers and boosters, which is number 1, followed closely by industrial machinery and unlicensed spectrum. So, okay, last chance, everybody. If you have a common source of interference, please cast your vote. I'm going to close the poll and share those results. So passive PIM actually came up number 1 as 32%, followed by signal jammers and boosters 25%, and then a toss-up between industrial machinery and transmission from mobile carriers. So I'll ask the same question there. Does that surprise you at all, Eduardo?
No, it doesn't. It doesn't. Yeah, we have seen PIM as one of the problems, which basically people like to go through this technique of using the spectrum analysis to first detect if truly it's a passive intermodulation. Now, typically what we have seen is that if interference just happens in a very isolated manner, for example, in one site, most likely it's going to be due to PIM. So that's when a spectrum analyzer test is performed to detect if there is PIM. Now, if there are a cluster of cells that might experience interference, then most likely that's going to be an external type of transmitter, which can be those jammers or those amplifiers or boosters, or can also be the industrial machinery or transmission from other carriers.
Okay. Well, one question we have is, Eduardo, how important is signal demodulation for interference analysis?
I think it's key. I think it's critical to reduce test time. As the example that I briefly showed, basically with interference identifier and then with signal analysis on that interference, we were able to save interference hunting. So instead of going out and trying to hunt where that interference might come from and then pulling all these tests and doing the triangulation, so on and so forth, all that was able to get eliminated just by obtaining the signal analysis or the specifics of the signal. So as an example, I've been involved in some tests with some operators where they were having difficulties of transmitting on or launching WCDMA in certain areas. And when we were doing that testing, and actually they tried to launch those WCDMA for an extended period of time, and they just couldn't because of the presence of that interference. And they were actually hunting that with not too much success, but when we came in and make the test and actually were able to confirm that truly was another modulated signal, a GSM, and we were able to obtain the cell ID, and all these tests actually happen in 2-3 minutes. We were able to obtain truly what was the cause of the problem, and the problem shortly after was eliminated, because internally they were able to go through the process of sending a trouble ticket and basically resolving these situations. So I think it's critical, and it's even more important to reduce test time.
Okay. On your presentation, slide 5, you showed triangulation to identify interference, and one of the questions we had is, how easy is it to use triangulation in an urban environment?
Yeah, it's probably the comment that I made on the location aspect of interference analysis, which it's challenging, because we have to avoid as much as we can the reflection of signals. So that's why it's recommended to make those tests even in urban areas from a rooftop or open spaces, which are not common, or it's time-consuming. So it is possible, but we have to pay attention to multipath or reflections of signals that might give us some wrongful indication of the direction of the interference.
Okay. How does the VBW affect the trace?
So the video bandwidth, it's a filter of video that exists on the spectrum analysis. And basically the only thing that it does is it reduces, let's say, the noise that is on the trace. So in reality, it's going to reduce the variability that we have on power for the measurement. So that's basically what video bandwidth does. It's just a filter of noise that excludes or eliminates noise from the signal. You can view it as just for comparison purposes, as averaging the measurement in power. So basically, we're going to be able to have a smooth trace, although it's not an averaging, but it's faster because it's just a filter that we're eliminating the noise on the trace.
Okay. On one of your slides, Eduardo, you showed a picture of someone holding a log periodic antenna, and the PIC is labeled directional receiver. Is that different hardware being used than the spectrum analyzer shown doing demodulation on the GSM UMTS slide on the previous slide? Do you remember that?
Right. Yeah, no, it's exactly the same instrument. It's our base station analyzer, JD745A. It's exactly the same test set. The only difference is that the measurement, when we want to locate interferences, we just use JAGI or directional antennas, whereas when we're just looking for the overall spectrum, we use omni antennas. But that's the main difference. The main difference is the antenna, but it's exactly the same test set.
Okay, and this is a good question. If you have a cell site with a PIM issue, can it affect other cell sites in the area? And then can your method of detection pick that up?
Right. So if there's any PIM that exists, is it going to affect other cell sites? It all depends on how close that other cell site might be. If it's co-located, for example, if there's a situation or a deployment on a distributed antenna system, let's say a stadium, in which different cell sites, small sites, are installed, and one is experiencing PIM, and basically that PIM, since it's co-located, it might be affecting other sites. So the answer is yes. It's basically, it has to it depends on how close are the sites and the PIM that basically hits on the uplink or downlink of the adjacent cell site. Now, is it possible to detect PIM. It is, but it is on the instance where the PIM is generated. Right, so we have to be on the site in which the PIM is generated, make that test that I briefly explained of just looking or having the signature of the noise, deactivating or shutting down one of the transmitters, and then having the transmitter to look into the PIM.
Okay, we've got time for one question. It kind of ties into that last question. Is it possible to detect passive intermodulation with a spectrum analyzer?
Sure, it is possible. This technique that I briefly mentioned, and I explained. Let's see. Just want to go back. So it's in the material. I just want to go back to see in which there were a couple of the slides that I included here on this presentation explaining PIM and how PIM can be detected with a spectrum analysis. Those were, I believe, slides 13 and 14. But yes, it is possible. The only thing that might be needed is to have control of the radios, because we need to have high-powered signals to be transmitted on the feed line to generate or to create PIM for that matter, and then with spectrum analysis detect PIM.
Well, we are out of time. As I mentioned earlier, we will be distributing a link to view this presentation within the next 24 hours. Eduardo, before we wrap up, any closing comments?
No, just again thank everybody, and we will try to answer all your questions, or please let us know if you have further questions. Again, additional information can be obtained from JDSU on just scanning the code that I showed on the last slide.
Great. Eduardo, thanks for your time, and we had great participation from the audience today and attendance. Just want to thank everybody who did tune in today on our JDSU webinar. Have a great day. Thank you.